Good morning.
Good morning.
Today we will finish this chapter 10, and then we'll be ready to program. Okay. And last time we talked about the details of the element stiffness matrix. Everything is expressed in matrix form, and each coefficient is given, so you know the details of those element stiffness. Okay, so that is last lecture's task. Today we are going to talk about the right-hand side of the equation. So the stiffness matrix is the K on the left-hand side. K vector times the displacement, K matrix times the displacement vector is equal to, on the right-hand side, the force vectors. The right-hand side consists of three possible contributions. One is from body force, one is from surface traction, one is from essential boundary condition if it's not zero. Okay, but of course it depends on on the particular type of problem. Some of those the right-hand side vectors may be zero. For example, if for the particular problem the weight of the body is not a concern, then you can say there's no body force. That actually happens a lot, depending on the type of problem. Okay, and if there's no applied traction, then of course the second vector will be also zero. And if there is applied traction but no the essential boundary conditions are zero everywhere, just fixed, then the third term will also disappear. But when we talk about formulas, we will assume all those three things on the right-hand side may exist. Okay, so let's talk about the body forces. The body force term, if you refresh your memory from the weak statement of finite element in matrix form, it is the transpose of the shape function times the body force vector integrate over the volume of the element. Okay, so this is the body force term. Okay, let's look at this term and see what is the physical unit of that term. It is important to understand that. What is the unit for shape function? Is it in length, unitless, force, or what? Okay, let me give you a hint. When we say displacement is interpolated using the shape function, right? From nodal displacement. What is the unit of that? Length. This one?
Also
Length. So this one?
unitless.
Units. Very good. This one, body force. B, I mentioned it before. Don't know whether you remember it or not. I said the body force vector B here should be force per unit volume of material. So the unit of that is Newton per cubic meter or pound per cubic inches, something like that. So this is force per volume. dV is the volume of the integration element. So what is its unit? Volume, like meter cube or inch cube, right? So now, what is the combined unit?
Force.
Just force. So you need to understand that to have a clear understanding of that. So this is coming out to be a force. All right, and this expression is in global coordinate. And as usual, we will turn into local natural coordinate So the limit is from -1 to 1, -1 to 1. The length, the thickness, we assume is a constant, so it's t, we take that out. And this will be expressed as a function of the natural coordinate, and the body force is also in terms of natural coordinate. And a lot of times this body force may be just a constant, because like the weight per unit volume of material, if the structure is uniform, right, it will be a constant. And then dV, to translate into natural coordinate, we will have a Jacobian J, and then d theta d eta. All right, once here, now we can view this whole thing as one integram, and the expression is in the natural coordinate. So we can use the Gaussian integration. Because this is a 2D integration, you have a double sum here. I from 1 to number of integration points, j from 1 to number of integration points. And we have weight I, weight j. And then this whole expression evaluated at theta I and eta j. Okay? So n evaluated at theta I, eta j, and this is transpose. And then B vector again evaluated at theta I and eta j. And then the Jacobian itself, it could be a function of theta and eta also. Okay? Sometimes the Jacobian is just a constant. It depends on the mapping between the natural coordinate and the global coordinate. If the mapping is linear, then the Jacobian is a constant. If it's quadratic, then it is a linear function. Okay? And for our Q8 element, the mapping is actually quadratic. So this is a linear function. Okay? All right, this is pretty straightforward. It's a direct application of the Gaussian integration point, so it's very easy to handle and very easy to program. All right, that's that. Okay, if you look at the expression here, the dimensions. This is the transpose of that is 16 by 2. And this one is the body force. This is a vector, right? So is this one is 16 by 2. This is a vector, it's 2 by 1. So at the end, it should be a 16 by 1. So it is a vector. Okay? All right, now let's look at the surface traction term. The surface traction term is a little bit more involved. The metric is the most difficult derivation part of the whole formulation. Okay, the formula is the shape function transpose times t and then ds. And again, look at this. This is unitless. The traction means force per unit area, and this is times area. So at the end, the unit is just force. Okay. Therefore, if it turns out you have an element for a particular element, if, for example, this node, let's say for this node there is surface, there is a point force. So this is point force of, let's say P1 here in this direction, P1x. Here we have P1y, and these are point forces on this applied load. The integration at the end will give just P1x, P1y, like that. So you don't have to do the integration actually. You just put the point forces and each node corresponding and its corresponding nodal position. Okay? That's how to handle the point force. Actually, according to our naming convention, this should be P1x. This will be P1y. 1, 2, 3. This is actually 3. This is 3. Okay. 1, 2, 3, 4, 5, 6, 7, 8, like that. And that also means when you mesh the element, you better put a node at the location where there are point forces. Let's say if this is your body, there is one point force applying here. It's the best to mesh it so that this will be one of the node, so you can directly apply that. Otherwise, if there is point force here, you will really have to do integration and find out what's the contribution and distribute it into those nodal positions. That will be a pain to do that. Why not just put a node here and remesh it again? Okay. So if the point forces are on the node, you directly put those force component at the corresponding nodal position, and that will be it. Okay. And actually, all commercial software, if you put point forces at certain location, it will be meshed in that way. There will be node at those node application point. All right. What about surface? Real surface tractions this time. And the formulation is a little bit more involved. Let's say this is the boundary. We assume this is x direction. This is y direction. The unit vector is E1 in this way, E2 in this way. Okay, these are the unit vectors pointing in x and y directions respectively. And this is the 3 nodes on an element. Let's say this is the element. Oh, there's no line here. But the QA element, it is possible to map curved boundaries because it's parabolic. Okay. Now, let's say we mark that at node 1, this is node 2 and node 3. All right, this boundary line will be called, the curve is L1, 2, 3. Okay, and then these are the surface tractions. T. Okay, let's put a generic point here. For this generic point, locally there is the normal direction, and there's the tangential direction. Oh, we draw that and call that ET. Okay. Well, in my lecture, I use ES. S indicates the boundary surface. So S, that's also fine. Or some books use S as the path coordinate. That is the path coordinate. Okay, this is an integration along a curved line. All right, from geometry. ES, the unit vector ES is actually equal to this one. If you decompose this E1 and E2 into ES direction, you can see that this is this angle. Okay, let's call this angle theta. In x direction, it will have E1 and then negative cosine theta plus E2 and then sine theta, right? This is just geometry. This direction, if decomposed in x direction, it has this component. In y direction, it has that component. And then, because we can also draw a triangle, this is ds, this is dx, this is dy. Actually, this is negative dx. If you draw this triangle here, you will have this kind of relationship. Using that, this is theta, this is exactly, cosine is exactly this over that. So it's negative, and the cosine itself is negative dx over ds, like that. Okay? So we can just get rid of this negative sign. Because when you go this way, dx is pointing this way, it's negative. Okay? Itself is negative. Then plus E2 times sine theta. Sine theta is obviously dy ds. Okay, so this is the tangential direction of a line element here. Now, the normal direction you see here, this is tangential. If you take this tangential direction and cross the out of plane normal, you will get this vector, right? Because the 3 forms a orthogonal set. So this thing times that, by definition of a cross product, one vector cross another one, you get this vector. So which is exactly the n vector, is equal to E as vector cross E3. All right, so let's put this in. This will be E1 vector dx ds. Let me just write it this way. dx ds E1 plus dy ds E2, and then cross E3. And then you put this in, E1 cross E3 is what? In a Cartesian coordinate,
Minus E2.
minus E2. It points to E2, but it's minus. So the first one is minus E2, dx ds E2. E2 cross E3 is
E1.
E1. So there's the cyclic thing. dy ds and then E1 vector. All right, so that's the expression for the normal component. Once we have these two expressions, now we can express the traction in the local, normal, and tangential directions. It's always convenient to do that, okay? When we solve a problem, any boundary, we will usually say, okay, the normal component is how much, the tangential component is how much. It's much easier this way than to say, I have an angle here, I need to times a sine cosine to find the x component and the y component. That's a little bit more difficult. All right, so now let's express the surface traction, which is a vector, is equal to the normal component along normal direction plus the tangential component along tangential direction. Okay? Therefore now we can say this n vector transpose times t vector ds is equal to the thickness. This t, I'm sorry for the confusing notation here. This t has nothing to do with traction. That t is the thickness. Okay, so we bring the English because thickness starts with t. All right. So ds, which is a surface element in 3D, if this is the curve, ds means this ds times the thickness. So ds is the area. Okay, and then now we still have this n transpose. Now we want to write this traction in matrix form. Okay, so we have Tn component, and the n is normal direction. It has x component and y component like that. So we can write it in this way. So this is dy ds, which is the x component, and the y component is negative dx ds. Right? So this is the n vector in x and y, the x component of n vector and y component of the n vector. And then we have the tangential component times this vector. This es vector, x component is that, y component is that. So it is dx ds, and then dy ds. Okay. And again, this s at this point is the arc length, and this ds is the surface area. Okay, because why it becomes arc length? Because we already take the thickness out. All right. With that, we can then write this here and transpose. We can combine the x component and y component together times, as you can see, now I take this times that plus this times that and times that. So this ds will cancel this ds and will cancel that ds, right? So the first one here is Tn dy, because ds cancels that, and then plus Ts dx. And the second one here is negative Tn dx plus Ts dy. Okay. Like that. If we write it out in full, remember this n matrix, when you transpose it, it is tall and narrow. So it has n1, 0, 0, n1. n2, 0, 0, n2, up to n3. Okay. We are talking about that section. It only has 3 nodes. So it's n3, 0, 0, n3. And then times this, which has Tn dy plus Ts dx minus Tn dx plus Ts dy. Okay? Alright, now I can erase this. Where for the Q8 element N1 is the shape function for the first node. Shader is equal to the 1D shape function where N1, N2, N3 are 1D shape function for 3-noded element. Like that, we have a 3-node, and N1 is a function of Chater, then it is half Chater minus 1. This is actually from chapter 5. Okay, we talk about this 1D element because now we are integrating on the surface of a 2D element, which is a line integration. N2 Chater is equal to 1 minus Chater square. N3 Chater is equal to half Chater plus 1. Okay, remember we talked about 1D element before, and we also have 2D. It becomes 1D because when you are talking about surface traction, a 2D surface is a line, so it is a line integration. Okay, and with that, we can say if you take this is 6 by 2, and this is 2 by 1. So at the end, you will have a 6 by 1, which is a 6-component vector. Okay, let's say, for example, f1x will be equal to, we will take the first element here, which is equal to this times this and add it together, will be equal to t times n1 times this guy, tn dy, plus n1 ts dx. How to integrate that? Okay, this is global coordinate, and then again when we do the integration we use natural coordinate. So it will transform this into -1 to 1, and the n1 is a function of Chater, like this one. And then we integrate this. Okay, I have to explain one more thing. dy, how do you do dy? We transform this into natural coordinate, right? Well, we will map that again as what is the relationship between y and Chater? Well, we use an isoperimetric mapping So x is mapped to from the nodal position I, x, and then xi. I is from 1 to 3. And remember, we have these 1, 2, 3 points. So this is x1, x2, x3. And then we assume in between any generic x is mapped from the nodal x using the shape function to do it this way, right? And here I should really write it as function of theta. For example, here theta is equal to -1, here is 0, here is 1. In between is like this. And similarly, y is also ni theta yi. I is from 1 to 3. Okay, so let me erase that. If that's the mapping, then dy, look at here, actually y becomes a function of theta, the natural coordinate. X is also a function of theta because these are given positions, which is not a function of theta. So dy, using the chain rule, dy, because this is only a one variable function, so we can use full differential. So that's the formula to estimate dy. And with that, dy d theta, put this in. Now we can say ni, differentiation of ni with theta, this is theta. And I from 1 to 3, all these together, and then d theta. Right? And dx, times iy. Don't forget that. We have iy here. And then this will be dx, d theta again. This is the chain rule. But because y is equal to that, we can move the operator inside, which operate on this shape function only, not on yi. Similarly, this will be like this. I from 1 to 3, d and I theta, and then d theta times xi. All these together and times d theta. All right, at this point now you can see when we plug this into here and this into here, everything now is changed to the natural coordinate, theta. Okay? Therefore, f1x, now put these two into this. We will have the thickness, integration is from -1 to 1, n1, which is already a function of theta. Tn is prescribed. It could be a function of theta or could be constant. And then dy is this guy. So we have I from 1 to 3, d and I theta, d theta times yi. Okay, and then times d theta, which I'm going to take out. Then let me write the second term. The second term is n1 theta ts, and dx is this guy, d theta. So I put this in. I from 1 to 3, d and I theta, d theta, xi. So all these together and then d theta. All right, up to this point, now you can apply the Gaussian integration now. Because the limit is from -1 to 1. So it's already natural coordinate with respect to that d theta. And everything inside the curly bracket here is simply a function of theta, right? So you can view these as like a g function of theta. And integrate a function of theta 1d using Gaussian points, pretty easy, right? So we can write it as t and summation. Because I already use I here, I better use a different index. Let me use it J. J from 1 to Gaussian integration point. So N1 theta J Tn times I from 1 to 3 and D and I d theta evaluated at theta J times yi. Then get all these together plus this term, which is Ni evaluated at theta J Ts summation I from 1 to 3 dni d theta evaluated at theta J and then xi. Alright, all this is that function evaluated at theta J. Don't forget the weight, Wj. Okay? So this is the surface traction integration. And it is a little bit involved than the body force term. Actually, in the textbook, only this is given. This is not written yet, but just one more step, you will get that. Okay? So that may be useful when you program it. So write that down. Okay? Now, there's a third possible contribution, which is the from the essential boundary condition. That again is a little bit. It needs some special treatment here, and for some reason I'm not in the textbook. It is not given here, but essentially it's the same way when you, because it involves those D matrix and B, so it's very similar to the calculation of the element stiffness matrix. You just move it to the right hand side. Okay, so we will leave it up to when the program up to programming time. Okay, we will talk about it. But the important thing is know how to handle the traction integration, which is the most difficult, and the body traction is a little bit easier. Okay. Well, I promised last time this is a short lecture, and that's it. We concluded that there is no homework assignment for this week. You need to finish the installation of the software. You done that, right? And John?
Yep.
You have done? You need to do that. Okay. I send out instruction. You need to get a login account from our department.
Yeah,
Have that. So you just go. It takes some time, okay?